Hello, and welcome everyone to our webinar Accelerating Fusion Reactor Design with Cloud-Based Multiphysics Simulations. My name is Jukka Knutinen, and I'm the head of marketing here at Quanscient, where we have a cloud-based multiphysics simulation software called Quanscient Allsolve. In today's webinar, we're indeed going to be focusing on the combination of fusion reactor design, HTS magnets and stellarators to be specific, and cloud computing. So in essence, we're taking a look at what's possible with the capabilities provided by cloud computing in HTS simulation and what that looks like in real life. Furthermore, we'll see how modern formulations such as the Thinshell method enable more efficient design. For this, we have a demonstration of our own by our senior solutions specialist, Dr. Lyly, and some real-world customer results from our special guest speaker, Dr. Nicolo Riva, magnet engineer at Proxima Fusion. Now, let's quickly go through our agenda for today for some extra details. So right after this opening section here, I'll give the mic to Dr. Lyly, who will first give you an overview of multiphysics simulations and their challenges in the context of fusion reactor design. After that, he will introduce the Thinshell method we have implemented in Quanscient Allsolve, which basically allows for the efficient modeling of thin layers in complex geometries without the need for explicit volume meshing, especially useful in Stellarator simulations, as we will soon see. So indeed, Dr. Lyly will present a live demo of a Thinshell simulation sweep in Allsolve to see how the, and I quote, Thinshell conductivity affects magnetic field development in an uninsulated spiral magnet. The live demonstration will also be an excellent opportunity to simply see the Quanscient Allsolve platform in action. Everything from importing and setting up the models, defining materials, assigning physics, all the way to visualizing and analyzing the results. After that, it's time for arguably the most awaited section where we invite our special guest speaker, Dr. Nicolo Riva, on the stage here. Dr. Riva will first of all introduce Proxima Fusion as a company and get everyone up to speed on what they have been working on. And after that, dive into the challenges they have been facing with their Stellarator and HTS magnet design, many of which you will likely relate to, and detail how they have been using Quanscient Allsolve to tackle these challenges head on. In addition to that, we will of course see some of the actual results that they have achieved with the tool, and even further see the workflow that they have been using to achieve the results. Needless to say, there will be some really exciting stuff coming up there. After that, we'll have our Q&A section where we address your live questions before wrapping up with a quick summary at the end. If that sounds good to everyone, without further ado, I'd like to give the stage to our senior solution specialist, Dr. Nicolo Riva. Take it away.
Thank you very much, Jukka. Hello, everyone, from my side as well, and welcome to the webinar. My name is Nicolo Riva, and my background is in electromagnetics, computational electromagnetics, and I did my PhD at Tampere University 2015 regarding superconductor AC loss and modeling those. So let's go to the topics. Today I will talk about challenges faced in modeling fusion applications and give a short introduction to the Thinshell method we have implemented in Allsolve. And the goals of the presentation is to highlight the challenges and the origin of those, give the background to the Thinshell method, and demonstrate the benefits of the Thinshell method over the volume-based modeling. And also I want to show how does the Thinshell conductivity affect the ramp-up dynamics of a partially insulated coil. So, origin of challenges. You are very well aware of this. So, they are typically the high aspect ratio and the large and complex geometries, especially in fusion field. Here we have a couple of examples. The other one is a Viper cable example you can see that there are HTS stacks embedded in conducting materials, and the cable is twisted itself. And typically the superconducting tapes can be, the dimensions are less than 1 millimeter, and then the aspect ratio, if we would take the individual tapes into account, it's huge compared to the cable itself. And easily, if we want to increase the details to the geometry, we will end up having huge problems to simulate. And typically it's not even possible, and we need to do some homogenization there for the tapes or the stack level even. Then here's another example of a stellarator geometry. This is a project by Proxima Fusion, and in this case you can see the aspect ratio as well. We are talking about several meter diameter of a magnet, and then the cable, the superconducting stack itself is around 12 millimeter. And even though it would be homogenized, the problem becomes really big easily due to the complex material layers around the cable. Also, the geometry is very complex, and there's no way we can exploit symmetry there, so everything needs to be done in 3D, and the problem becomes easily very big. And before I go any further, I really would like to thank Proxima Fusion and Athlete Engineering for this really interesting collaboration project and opportunity to participate that. Then what can we help to improve the accuracy of the models? And the possibility to take into account more details in the model. One option can be Thinshell method. And 2022, here on the right, we can see the basic idea of the Thinshell method. It was introduced by Alves et al. At Montreal, and there's the general idea behind is that we can, in 3D, we can present thin volumes as surfaces, or in 2D, we can represent surfaces as lines, and this will reduce the complexity of the geometry and CAD, as well the meshing significantly. And the method behind is to introduce a virtual finite element problem for the Thinshell domain only. And fields inside the Thinshell, they are approximated using linear basis functions. So on top of H-phi formulation, we can introduce a new Thinshell formulation for the thin surfaces. So what we have done is we did simulation to compare the Thinshell method against the volume-based simulations. And you can see the geometry here on the right. The blue one is a cable spiraling around, and it has a thin volume layer around it, and everything is embedded in steel structure. Here on the very right, you can see the very thin conducting layer around the cable. And everything is meshed in the volume-based approach, and in the Thinshell approach, we neglect the green area, so it doesn't exist in the model nor in the mesh. And here's the result on the left regarding the mesh. You can see that for the volume-based approach, where we really have the actual volume present, we need to do very fine mesh also in the cable in order to have a decent mesh in the thin layer. Whereas when using Thinshell method, we don't need this additional thin layer at all in the model, so we don't need to refine the mesh in the cable so much, and we can easily reduce the size of the problem. For example, in this case, with this mesh we had 5.6 million elements in the volume-based mesh, and for the Thinshell mesh only 0.59 million elements. And when solving the problem, it resulted in 0.7 million unknowns for the Thinshell method, whereas we had 5.5 million unknowns for the volume-based approach. Here are some details. Cable was 6 times 6 millimeter, and the thin layer was 0.1 millimeter thick. And in this case, the mesh with respect to the domains on both sides of the Thinshell, it was conformal, so they shared the same nodes. Some results. We did 3 different simulations. Simulation cases, and in the first one, the conductivity for the Thinshell was very high. We wanted to see that the current is flowing in the Thinshell and to compare the net currents between the different models. So in this case, we had the cable conductivity the same as in steel. And on the leftmost figure, you can see the magnet field dynamics during ramp up. So the red curve is always the applied current, and we can see that there's a delay in the magnet field rise up. Then we have the losses and the net currents in different turns, at the very top turn and in the middle turn. You can see that the models are matching pretty well. There's only 5% difference in the losses and less in the other quantities. Then second case, we introduced a pore conducting material for the Thinshell, and also the volume, of course, for the thin volume. And here are the results for that. They are almost in perfect match in this case. So the field is rising in the same rate as in the both models. Also the losses are the same. However, you can see differences now in the net currents. However, if you compare the amplitude of the current, it's negligible to the applied current. So this basically noise level signal in the Thinshell, and this can be really affected as well by the mesh. So the mesh is not that accurate in the Thinshell model anymore, since we are using bigger elements there. Case 3, we increased the conductivity of the Thinshell. So now there's more a better path to bypass the cable in this case. And from compared to the last one, you can see that already the ramp up time is higher here. Before it was 30 seconds. Now it takes 50 seconds to achieve the stable conditions for the magnetic field. And again, you can see pretty nice match with the two models. And here, now in this case, the losses are a bit different. But now the losses are negligible to the losses in the cable and steel again. And they are almost negligible in the model. So as conclusion, the Thinshell method agrees very well in this linear comparison we made against the reference simulations with volume-based model. In these cases where the investigated quantity was almost negligible, then the correspondence between the models was not that good. If we compare the simulation times, for example, in this 50-second case, it took about 2000 seconds and for 26 nodes for running the volume-based model, and half of that for the Thinshell simulation with only one node. So here you can see already a big difference in simulation time, and you can save many core hours as well using the Thinshell method here. Finally, before going to the demonstration, here are the field plots for the current distribution in red here, the red arrows, and also on the slices you can see the magnetic field distribution. And this is the second case we studied, and you can see that also visually there's a nice match between the two methods. So let's go to the demonstration on our platform. So here is the geometry, and I can also introduce quickly how to set up the problem. So if you are not familiar with the product or the simulation platform yet, I will quickly go through, and in case you need some more details, you can also check the previous webinar we had. It's a similar simulation case. Okay, so basically here we have imported the coil geometry, which is here. So you can import step files or build from scratch. And here we have added air around the model using the operations we have available in the editor. But if we check about the materials quickly, I will hide some domains first. So this is the one using Thinshell method. Therefore, we don't have any, if we zoom in a little bit, we only have the cable embedded in steel. And in the formulation, we apply the Thinshell approach on the surface now. So we don't have the volume at all in the model. So we had the airbox, then we have the steel and cable in this Thinshell model. Also, you can add additional surfaces for post-processing if needed. For example, the surfaces for integrating currents, net currents through the winding. As well, here you can introduce the simulation parameters. So we have the transport current, the amplitude of that. We apply a ramp function. And then we have the three conductivities. And once they are defined here, we can sweep over the variable later in the simulation section. So here we have the cable conductivity as 1e12 and steel 1e7. Then in the physics section, we define H-phi formulation. And H is for all the conducting domains. Then phi formulation, the scalar potential is only in air, in non-conducting region. And we constrained the potential to have unique solution. And here, using the cuts, we can introduce net currents to the model. So basically, it goes like this. You only define a loop around the conductor where you want the current to flow. And I want to emphasize that the flexibility of the software. So, for example, let me show this from the phi point of view. We have basically two holes in this modeling domain, which means we need to introduce two cuts to apply currents. And for the non-insulated winding, we even don't know what the current is. But in Allsolve, this has been done automatically behind the scenes. So the user only needs to define the current which are known. So you want only to address the current to the cable, and we automatically solve for the currents behind the scenes for the unconstrained. And this is very convenient feature when you are having a really complex shaped geometries such as Stellarator. So you don't, in the CAD, you don't need to take care of anything regarding the unconstrained currents. Then in the simulation section, let's make a copy of this old one. So you can see here we have the meshing options. And the mesh looks like as it was in the slides. You can visualize it here. And then we can do a sweep over the conductivity here. And what I forgot to mention, we don't yet have the Thinshell in the GUI available. We will package it after some more testing, but in future you can add it here as you would add electrical insulations or something else. But now we have implemented the Thinshell via scripting interface, and we will do it more convenient for you later. So let's do not go to the details of the formulation. I will just show how to run a sweep over the conductivity. So we can input the Thinshell conductivity here and choose the values we want to run it. And we can also output currents, losses by adding them here. So let's run the simulation. We can follow the simulation in the logs. And I can show, before it starts, I can show some parameters here. You can choose your simulation type here, then the solver type, and initialize the time stepping parameters. And we have two options for the solvers. We have direct solver and the iterative. And the iterative one is based on the DDM, the domain decomposition method. And especially when you have nonlinear materials, it can speed up a lot the simulations. So basically, behind the DDM, we split the mesh in pieces and solve all the pieces parallel, and the information is changed only on the surface layers of the sub mesh pieces, and this can scale up the simulation time significantly. Here you choose on how many pieces you divide the problem, and you can choose the node type. If you need more RAM, you can choose a bigger node, or you can just increase the node count. And here I think we have something starting. You can see all the jobs, they start simultaneously, and here you can follow the progress. So you can see we have two cuts, one unconstrained and the one we set the current through. We can see how many unknowns we have, and in this case we can run it with one node. And typically the bigger the problem is, you can increase the node count and see the scaling appearing there in when checking the simulation time. And now we can see the time steps, what it's taking. And we can go to the live plotting and start seeing some results appearing. And the most interesting maybe for this is the ramp up dynamics. So here I'm plotting the magnetic flux density in the bore of the magnet. And we can also add a current there to see. Let's put the bore field on the right axis. So now you can see how does the change in conductivity affect the magnet ramp-up dynamics. Here the dotted line, it's the applied current, and then you can see the colors. The first one color here has the lowest conductivity, and if you follow the curves, you can see it's behaving almost linearly now. So we addressed almost full insulation for the Thinshell. So all the current wants to go to the cable in that case, and you can see almost linear behavior in the magnetic field. Then if we start increasing the conductivity of the thin cell, the current wants to go during ramp up, it wants to bypass the cable easier. And you can start seeing some slopes there. And the higher the conductivity is, the bigger delay you can see in the magnetic field ramp up time. We can also plot the losses. So, for example, in the cable, and then we can see the losses behaving. First, we have eddy currents appearing, and we ramp up the current in 10 seconds, and then you can see some stabilization in the losses. And this will run up to 30 seconds. After that we can see some field shots from there. We can also investigate the losses in the thin cell. And again, after we have ramped up the current, you can start seeing decrease in losses because the currents, they are going to the cable. And also here, since in the first case we had almost full insulation due to the bad conductivity of the thin cell, almost all the current goes directly to the cable and stabilizes there. And in cases you have a higher conductivity in the thin cell, you see that the current, after current ramp up, the current starts to redistribute inside the winding and wants to go eventually to the cable. So you can see that after current ramp up in these cases with higher conductivity in the thin cell, you can see it. Okay, now it's current is increasing kind of in the cable now. You can see it as in increase in losses as well. And here you can also see that by changing the conductivity of the thin cell, the actual stable conditions are not exactly the same as you would have with fully insulated cable. So there's some currents always bypassing the cable in steady conditions as well. And this is regarding, for example, the Stellarator design. With this thin cell method, you can affect how does the magnet dynamics behave, and you can build more accurate models so that you can have even maybe more elements in the cable, because you don't need to really mesh the thin volumes. And if you want to consider partially insulated cases, and if you can affect the conductivity between the cable and the steel around, then you can use this Thinshell model to check how would it affect the magnet ramp-up dynamics. But I guess we can stop the simulation here, even though it's pretty close already, and we can visualize quickly the magnetic field distribution. Or do we have it available? Not yet, but okay, I ran it before already. So, for example, let's refresh. For example, the current current distribution let's reload the solution. You can visualize the currents here also in the steel, if you like. This is at the final stage, and also, for example, the field magnetic flux density on the cable surface itself. And if you would take the plots during the ramp up, you would see how does the current start distributing inside the steel volume. But basically this was everything I wanted to show for today, and thank you for listening. And I will give it back to Jukka and Nicolo next.
Thank you, Mika, for the wonderful presentation. With that, ladies and gentlemen, it's the moment we have all been waiting for, as I will soon give the stage to our special guest speaker, Dr. Nicolo Riva. So Dr. Riva is a magnet engineer at Proxima Fusion, where he specializes in simulating and modeling HTS magnets, particularly REBCO, for their application in Stellarator fusion reactor design. He holds a PhD in electrical engineering for applied superconductivity and has experience from his postdoctoral research at MIT, collaborating with organizations such as Type 1 Energy and Commonwealth Fusion Systems. So, without further ado, please give a warm welcome to Dr. Nicolo Riva from Proxima Fusion.
Hello. Hi. Could you hear me? Can you hear me properly? Yeah. Okay, great. Sorry. Just to have a heads up. Okay, now you really have high expectation. You've been way too kind with me, Jukka, but I will try to keep it up. Thanks, first of all, for the occasion. It's a pleasure because it's a collaboration that we started quite a while ago, and maybe I will talk a little bit about this. But first, I would like to show with my presentation where let's say where we are with Proxima Fusion and how at the end of the day we are using Quanscient Allsolve to enable our simulations. And to do that, I will also try to reply. I would like you to go away with three research questions to reply to. First of all, is what are the challenges of modeling HTS stellarators? And then more specifically, with regards to the seminar, how Quanscient help us to tackle those challenges, and in fact, what is Quanscient for us as Proxima Fusion? And to do this, I'm going through 3 sections. The presentation is in 3 sections. It's first, again, about Proxima Fusion, then the challenges, and then the specific case of simulation that we did with Quanscient. So, first of all, Proxima Fusion and the path toward an HTS stellarator in Europe. Proxima Fusion, it's one of the various startup for fusion, but we specifically are a spin-out from the Max Planck Society, which is the Max Planck Institute of Plasma Physics. It's a quite unique place that had 6 years of fusion R&D. And in fact, Proxima HTS Stellarator are enabled by groundbreaking advancement in both the Stellarator and the HTS world. Stellarator with the recent results from W7X, and in terms of HTS by the groundbreaking results that HTS has shown to achieve with the Spark program at MIT and CFS. And why HTS and why Stellarators? Probably most of the audience do not need to be convinced about this, but in short, the fact is that magnetic field really really sets the size, cost, and time to build a magnetic confinement fusion device, because the power output is proportional to the 4th power of the magnetic field. And at the end of the day, HTS really enables to achieve very high magnetic field while reducing the volume of our machine. So it becomes more compelling from a commercial standpoint. Why Stellarators is because we prefer design over control, which means, as many of you may know, in case of magnetic plasma confinement is achieved by helically twisting the magnetic field lines, and tokamaks do this by using a combination of multiple coils, so on, and the solenoid. At the end of the day, it's what is needed. It's used to twist the helical field lines, and to do this, the central solenoid needs to be pulsed. And being pulsed, this leads to plasma disruptions eventually, and which means that tokamaks are really it's a pulse machine. It's not a steady machine, while Stellarator inherently are more stable because the coils, the shape of the coils is what give the helical twist. So that's really interesting. Of course, on the one side you have tokamaks that are easier, but harder to operate, while with Stellarator are much harder to build, but in principle easier to operate. So that's why specifically HTS Stellarators. And in order to get there, this is what our timelines looks like. We recently achieved one milestone that was the conceptual design of our reactor, and it's been submitted for peer review. It will be soon published, so stay tuned. But we are ramping up in terms of magnet design and hardware prototypes, and the goal is really to build a demo magnet by 2027, which is going to be some subscale of the first prototype of Proxima. It's called Proxima Alpha, and we aim of doing this by 2031, and then by mid-2030s, we want to build the first of a kind fusion power plant based on Stellarator HTS technology. And we call it Stellaris, and that's also how you will find the paper online. Okay, fabulous. Now let's get to what I'm interested in and what I love the most. It's really HTS materials. And, when it comes to HTS materials, there are a plethora of challenges that we have to face with. And those are just some of the key challenges that you can think of. There are many more, but I like just to mention some. Of course, besides the classic trade-off between amount of stabilizer and compactness of the cable, you have something much more peculiar of fusion reactor, like the neutron flux impact on HTS. And how does this material really behaves in longer terms? It's something not very, very clear, and luckily researched by a few groups around the world. There are things like the classic quench mitigation strategies, mechanical strengths, and of course multi-scale and multiphysics. That and the last three are the one that I'm going to talk about. So how bad multi-scale and multi-physics could it be when we look at fusion reactor like this, Stellaris? So let's imagine that Stellaris is something like 16 to 20 meters diameter. Then each of the coil is about 3 to 5 meters. It's composed of several turns, like 200 to 300 turns of HTS conductor cable. And then we had this is what conductor cable typically look like. It's composed of copper and an HTS stack. The cable is around 15 to 20 millimeters. Then there is the HTS stack, 4 millimeters, and then we go down to the stack. This is very much what Mika presented before, so we shouldn't spend too much time on this. And then when it comes to this, I'm controversially, I would like to use one quote, and that is from George Box, and it's very famous. All models are wrong, but some are useful. And I would like to take this chance to remember that why our models are useful, because it's much more easy to design, to do iterative design without manufacturing. It's manufacturing is clearly fast, but sometimes you really need to model in advance to be sure. There is a trade-off between optimization, cost, and efficiency. You can predict your analysis, but then of course the models can really be wrong. And this of garbage in, garbage out means that we don't know what to put and we don't know what we look at. There are real-life material homogeneities. And then, again, to stress again the point of the slide before, such models are hard to scale and are highly nonlinear materials. So maybe the point is Quanscient Allsolve can at least help on this and significantly boost the accuracy to achieve these valuable results, thanks to the tools that Mika, at least in this seminar, Mika presented. And so let me get to Stellarator models with Quanscient Allsolve. Probably some of you in the audience already saw this slide or something similar. So it's very messy. The takeaway message is that needs to be messy. We receive a lot of configuration from the Stellarator optimization team, and then we need to iterate and evaluate multiple things that range from the magnetostatic structural quench modeling and so on and so forth. And at the end of the day, we need to get to the end where we deliver a design and that tells us how much current we can put, what is the stress, and so on and so forth, and what's mechanical loads, and so on and so forth. And it's a very complex problem. And here I forgot to mention a couple of papers and a couple of resources. This is it's an interesting active area of research. Other people are working on that. There are a couple of people. One is from EPFL SPC, Daniel Biek, and someone else from Torino, Martina Gascello. I think they did something similar, but open source, and so that's very interesting. Now we're trying to do this with combining multiple tools. And maybe I would like to give you the first example where Quanscient really help us. When I'm saying that we need to iterate several things, imagine that we get one configuration from the Stellarator optimization people, from a plasma physicist, but then they come up with a second configuration, and then a third configuration, or nth configuration really, and then we have to deliver some mechanical analysis. And in fact, this can become really detailed down to a sub-level cable. And this iteration occurs on a weekly basis, or sometimes even less. And how do we keep up with this? And especially, how do we do magnetomechanical model integration? We did some preliminary work once upon a time. It was a few years ago. An excellent work done by Merle Bachmeier, where we did this model of a full Stellarator, where we were evaluating both magnetic field and forces. And a paper was published if you are interested in. The thing is, it was a little bit cumbersome because Mika and Merle knows very well. There was a lot of efforts in clicking the boundary conditions and so on. And if we have to change the configuration, we have to do this all from scratch. So it's very complicated. And so now we have something is called really the Quanscient API, and it's an almost one-click solution for magnetomechanical study of any coil and Stellarator configuration. I'm saying almost because it still requires a lot of work of meshing, of course, on our side. But the idea is that on the one side you have the user that uses CAD, that just has to provide CAD, mesh, and a script. in Python, or it's in Python. And on the other side, Quanscient Allsolve does pretty much most of the things. Ranging from some sanity check to the full Stellarator B field and magnetomechanical analysis. And in short, I just want to show the workflow because we don't have much time. On the one side, the user really has to set up the basic things from the Python script to the mesh and the JSON file with what we call tagging, because we need to tell clearly which domain is what. Like if we do the mesh, if you're familiar with Gmesh or so on, you will have to tag a domain or a surface or a bound or a line or so on. And then once you do this, the idea is to upload all this thing and to let Quanscient really run most of the things. This work was done in collaboration with Athens Engineering, as Mika also mentioned, which is Tara Benkel, really, and then we go to the second part, which is really what initially was mentioned by Mika. So specifically, the classical question that when it comes to this monster coil that we need to keep asking is, do we need to model quench at large scale? And in short, when it comes to insulated coils, it's not really the case, because as most of the community is aware, we can use well-established and proved models like mites, electrothermal models, lamp models, and so on. But then there are other problems such as screening current-induced field, which are very problematic for field quality or induced stress that require 3D simulation. So it's not always obvious that insulated coils are fully let's say, unaffected by large-scale quench or large-scale modeling. And then we have a classic case of non-insulated coil that it's very attractive for stellarators due to their DC behavior, but then they require large-scale and high-fidelity numerical simulations. And in the case of Stellaris, we opted for no insulation approach, which means, we need to model quench at large scale very much. And so let me go through an example. And this is non-insulated non-planar double pancake. Here you see the double pancake. You see the current leads. You see the unit cell that's composed of HTS, copper, solder, and steel. So this is one of the classic unit cell design for non-insulated coil that has been recently developed. It's double pancake. Here we have a perfect insulation layer, so it's insulated between pancakes. And then what we want to do is really to ramp up the coil, similar to what Mika showed. And then we have some intermediate step, and which is still transient. But we specifically what happens is that during the ramp up, we use linear materials to speed up the charge. And then we switch to nonlinear materials. And to do this, we need some current distribution. Then we are fine where and so at the end of the day, what we want to do is place a defect, at some point detect quench and ramp down the current. And this is pretty much what we did. I'm showing you here the positioning of the defect, which is a dip into the first turn really, or the first few turns. But here is not very clear from this map, but it's not a radial defect. It's and then once we did the defect positioning, we after the ramp up, we do the ramp down. First we do the quench, quench detection really. So we let the current going and heating the surrounding region, and then we do the ramp down. In fact, although we do the ramp down, and here you see the current that goes from it's an outstanding 80 kiloamps down to 0. You see the magnetic field on the right, and here the magnetic field is still pretty much constant. With it's similar to what Mika showed, but reversed. What I mean is that even if we remove the current, we still have all the energy stored in the coil, in the magnet, in the double pancake, and it will take time before the magnet is completely de-energized. We can look at the temperature rise around the defect. Here is just a temperature map. You see sort of hotspot or so on of 170. You see that the interested region is only the top pancake. In fact, the bottom one, remember, it was insulated. Maybe worth mentioning that the insulation between pancakes also was done with a Thinshell method, so to speak. It's a boundary condition. It's very convenient because, again, you don't have to simulate the whole like the very thin layer of Kapton or epoxy, whatever you put. And then you have the typical beginning of a quench avalanche that you have in non-insulated coil, for those of you who are familiar with that. And what I mean is that you have some current that maintain the current turn, some others that pick up, because you see, specifically in this simulation, you see the first and the last turn. In fact, the one closest to the current leads, that where the current drops, it's where we suck out the current, and then others picking up. So here we didn't go much further, simply because we already achieved basically hotspot temperature of the pancake, showing that was not very safe. So with this, we have to conclude this because we kind of run out of time. And in terms of wrap up, remember the research question at the beginning. What are the challenges of modeling HTS Stellarator? Well, multi-scale and large aspect ratios and geometries, nonlinear materials is pretty much a nightmare, and there are a plethora of methods to tackle them. But how Quanscient is helping us is really basically tackling large-scale problem as we need, where we cannot use specific symmetries. And one of the things that I really appreciate the most is the tailored solution that for HTS modeling that they've been developing, ranging from multivariable interpolation, from Python API, the Thinshell, and many more that are in production. And in fact, what is Quanscient for us is really enabling for these specific tools. And if I can open on this, there's quite a unique expertise and blend of people that have experience in HTS and advanced numerical expertise, cloud. So it's really something that I'm appreciating and enjoying. And they're open to challenges and really collaborative. So this is something I really appreciate. With this, I would like to thank Proxima Fusion, Athlete in person of Tara, Menkel, and all Quanscient for all the fun and for this project. Thank you very much.
Thank you, Nicolo. Amazing. And well, as you mentioned, we are kind of running out of time here. So as for the Q&A, we have only time for one question that I would actually want to ask from you, Nicolo. So the question goes like this. So a lot of people are very attached to their existing simulation software and find it hard to either find time or the energy to even begin testing a new platform. So how would you encourage these people solving problems similar as yourself to pull the trigger and try something new?
Yeah. Oh, I understand the hesitation. I understand a lot of hesitation to move away from tools. It's like, I don't know, WD-40 for the engineers, I guess. Don't move it. Keep it like that. It must work. I don't know. Maybe, well, few points. Maybe let me try to summarize. I don't believe there is a silver bullet. Similar to the hybrid formulations that Mika showed, you want to use the H in one point, the phi in another point for a very specific numerical region. Each tool has its own problem. But more specifically to our problem, so maybe the second point is you can say the same for the old bike. It already works, but you want to change it, you want to go fast, and I'm fine with the risk of struggling to learn new things, really. And in fact, and then maybe the third point, I don't know, as a researcher, by staying with older methods, you really might miss out innovations like this. It's really groundbreaking that could simplify your workflow. We saw that, automate repetitive tasks, and just at the end of the day, it's an investment for you and versatility in your versatility, and in because yeah, we live in a pretty competitive landscape, and I think it's just a great experience to learn new things. It's also for you.
Awesome. So with that, I think it's time to wrap up this very short Q&A section of ours. And I will give a huge thank you for our technical speakers, and especially our guest speaker, Dr. Nicolo Riva, and of course, Proxima Fusion as a whole. All right, so just to really quickly recap what we saw here today. So in the beginning, Dr. Lyly introduced us to some of the main problems facing HTS magnet and stellarator design, with the root cause for these being the high aspect ratio and large and complex geometries in general. We saw an introduction to the Thinshell method that is implemented in Allsolve, and saw a live demonstration of it with comparisons against the traditional volume-based simulation. So in essence, we saw how the Thinshell method was used to provide accurate results without the need for explicit volume meshing. After that, Dr. Riva introduced us to Proxima Fusion and the work that they have been doing, and demonstrated some of the quite impressive results that they have gotten with the Quanscient Allsolve platform, as well as the API workflows they are already utilizing. So, all in all, the aim of this webinar was to demonstrate how the industry of, well, pretty much HDS design as a whole is unequipped to handle these complex, large-scale simulations with the traditional desktop-based tools. Furthermore, we wanted to demonstrate how the innovation of modern cloud-based simulation software, such as Quanscient Allsolve, is used today to achieve results and outcomes that are simply unattainable with any other tool. Now, if anything that you saw here today sparked your interest and got you thinking about what Quanscient Allsolve could do to you, head on to the URL on the screen and tell us about your use case. For example, any specific challenges you'd like to solve, any particular aspects you're interested in exploring, or any specific goals related to your work where Allsolve could potentially help with. Our team will review your case and get back to you within one business day, detailing exactly what working with Quanscient Allsolve could look like to you. With that being said, I want to once again thank our technical speakers and, of course, each one of you guys for being with us here today. Have a great rest of the day, and we look forward to meeting you again. Bye-bye.